Let's say you work as a design engineer working on things like turbines or heat exchangers, and one day your manager walks into your office and says, look, you have until Friday, our project sponsor wants to see what kind of performance we can eke out of our product. And so you go, you sit down, you say, great, let me go ahead and optimize this thing that I have. You load up your geometry, your measure, you increase the fidelity, you increase the number of variables that you're going to need to optimize this thing to be able to eke out the kind of performance that you need, and you hit run. But then what happens? Well, your optimizer starts to get stuck in all of these local optima. It seems to explore all these areas of the design space that aren't super useful because it's trying to deal with the cursive dimensionality that you've imposed on it. Frustrated, you turn over to your friend in the CFD department who says, hey, have you ever heard of adjoints? In there, dimensionality is free. You can get access to gradients for very, very complex designs. So you say, this sounds great. So now you start up the adjoint solver only to realize that it's really difficult to get this darn thing to even converge. And when it does converge on the kind of chaotic flows that you're used to, it's also getting trapped in things like local optima. So this gets kind of frustrating. And then what you do is you say, okay, well, I guess I'll just have to give up on trying to increase the fidelity of the model because that seems to throw off my global optimizer. And I also don't think I'm going to be able to get access to gradients because the kind of problem that I'm using is not really amenable to adjoints. So, I'll increase the fidelity a little bit, eke out a little bit more performance, and just let the optimizer run until Friday. What you're seeing here is a sort of standard example of where you're making a fundamental trade-off between the flexibility and expressiveness of a design space, the number of design variables that could describe, for example, the complexity of a turbine or a heat exchanger, with the cost associated with optimizing very high dimensional geometry when you don't have access to things like gradient-based methods, which is very common in industrial practice. I'm here to tell you that there's a fourth way, or another way to think through this problem, which is to think through how can we reduce the number of designs variables to find just the number of variables that we need to get the expressiveness to find the right kind of optimization and optimal airfoils that we need. That idea is something called a design manifold. So today what we're going to do is we're going to talk through three basic areas. What are design manifolds? Why are they useful? And if you're interested in them, where can you go from here? So to understand what a design manifold is, let's revisit our turbine case before with the example of something like an airfoil, right? So in an airfoil, if you wanted to optimize this for some kind of performance measure, maybe that's lift over drag, for example, you'd have to describe what an airfoil is. And typically in this example here, we're talking about geometry, although things we're talking about could apply to other types of things as well. So if we look at the geometry of an airfoil, you'll notice that there's individual 2D points that correspond to the shape of that airfoil. And each of these is basically a variable that I'm going to have to optimize over. So when I talk about increasing the fidelity of the design space, that can be adding additional points that increases the flexibility and fidelity of the design, maybe ekes out greater performance, but also might be difficult to optimize. But if you look at it, even though this particular airfoil here, let's say it had 100 points in 2 dimensions, that's a 200-dimensional thing that I have to optimize, we kind of know that airfoils aren't actually 200-dimensional objects. And to get a sense of why this is, imagine we take each of these points and just perturb it just a little bit, right? Just move any of the variables, the sliders or the knobs that control the shape, just a little bit. And what you'll see here is, while it might look imperceptible to us, there's actually a big change that occurs here from a performance and flow perspective, right? You can't have this small amount of noise in the original representation. And so this gives rise to an idea that says, okay, well, maybe I don't want to use all 200 of these knobs. I can't ignore a subset of them, but I might be able to figure out what are the sort of subspaces that control all of them in a way that all of the airfoils that I care about lie on that subspace. That's the idea behind this thing called the manifold hypothesis. And the manifold hypothesis is basically that there's a subspace, a sort of a lower dimensional version of this space where all of the airfoils that I'd actually want to consider live. And what my job then becomes is, rather than optimizing all 200 dimensions, instead I'm just going to optimize along this little potato. I'm going to take it, I'm going to flatten it out like a map, and then find the right spots on the map that allow me to get to the high quality airfoil that I want to. And as long as we're able to find this subspace, we can do this. So what my group does is we investigate methods for finding these low dimensional subspaces. I'm going to show you some examples of that today. This is an old problem. It's been around for decades. Typically, people explore linear subspaces, so that's why everything is basically flattened onto some kind of hyperplane. The kind of things I'm going to tell you about today are finding nonlinear versions of that problem. So one way to think about this manifold hypothesis is the way that people think about images, right? So there's a bunch of work now on things like deep learning for images, where people can generate very high-dimensional megapixel or larger images. So what you can think about doing is just taking airfoils that you've seen, for example, the UIUC airfoils dataset, and just treating this as an image generation problem. What we show in our paper is that if you take a common model such as the InfoGAN, which is used for images, and just try and apply it to airfoils, generally speaking, it doesn't do well, right? After about 1,000 samples, you start to see things that vaguely look like airfoils, but as you feed it more and more training data all the way up to 5,000 samples, while they tend to better approximate airfoils, there's still all this noise that represents what I showed you before, minor variations that in image space would not be so bad, but in airfoil space can be the difference in huge amounts of performance. So what my group did in the paper that you see here, in our Bézier-GAN paper, is essentially take the original image generation pipeline, but now substitute in layers, differentiable layers, into that model that allow you to model engineering constraints that we care about. For example, things like continuity or curvature control, you can now do here. And what you get by this is now with only about 1,000 samples, you're able to get much, much smoother geometry. Right? Things that look like the kind of geometries that engineers would produce in SolidWorks or your favorite CAD package of choice. And that this only improves as you get a greater number of samples. So what this means is that you're able to, in much, much fewer samples, which with fewer data, be able to recover these shapes. This also works for multi-part assemblies, which are quite common in engineering. So for example, if you have a design, which maybe is an airfoil with some parts that need to be inside of it, we can actually describe sort of dependency structure, the way that you might create these parts, including which parts depend on which other ones, and then come up with new kinds of architectures that are able to model conditional dependencies between parts. In other words, how does the shape of the parent part affect the shape of the child part? And what you can do then is create conditional manifolds. In other words, conditioning on, let's say, the airfoil wing, what's the shape of conduits that I might be able to fit inside? And then you'd have to worry about things like self-intersections and other types of problems. But if you compare this to the kind of thing you'd get if you just treated this as an image problem, this is the kind of, if you just take multiple shapes and try to embed them in each other, what standard image models learn is a space that doesn't differentiate between part dependencies. It just treats them all as a continuously morphing space, which is very difficult if you want to do individual optimization over each of the pieces. In contrast, something like a hierarchical generative network would allow you to actually model each of the parts separately and learn interesting representations that you wouldn't have previously. For example, in this example here, where we made one part tangent to the inside and one part tangent to the outside of this larger shape, what it learns is actually polar coordinates as being a reasonable representation for both the inside and outside geometry, even though we didn't tell it ahead of time that polar coordinates is what we were going for. So it can come up with much more reasonable representations of the design space than if you just treated it as one big image to be generated. Okay, so that's to describe what design manifolds are. Why are they useful? Why would you ever want to use something like this? Well, the first thing is that random samples in Bézier-GAN space or B-GAN space just make more sense compared to other state-of-the-art methods. What I mean by this is if you take a look at samples from the UIUC airfoils dataset, you can kind of see what typical airfoils that these things have been trained on or can generate look like. If we look at samples that are just randomly sampling the latent space of a Bézier-GAN compared to randomly sampling that of singular value decomposition, which is kind of a linear decomposition that is also learned, or an eigenspace like modal variables, or something like freeform deformation, Bézier-GAN does a much better job of being able to constrain the parts to avoid areas where there are things like self-intersections of shapes. Right? So the sort of subspace it's learning is a lot more robust to perturbations than some of the other methods that you've seen. In addition to this, it also samples, randomly sampling in the Bézier latent space samples the kind of distributions that you see in other engineering applications or in the original database better than existing state-of-the-art. So for example, on the leftmost, you see the UIC airfoils dataset. That's the training dataset that we were using. And both Bézier and SVD train on that dataset, but Bézier does a much better job than single value decomposition at capturing that space. Likewise, modal coordinates as well as freeform deformation can produce geometries that are quite different than what you've seen before, and that can be good or bad. More importantly, optimizing on Bézier space improves optimization performance. And to see what I mean by this, I'm going to show you a bunch of plots that kind of look like on the x-axis the number of samples that you need. So these could be very expensive CFD simulations on the order of days or weeks. So in general, you're going to want to be using the fewest number of samples possible. And on the y-axis, we're going to plot optimal lift over drag. This is some performance measure that I'm using for airflows here. This can be another performance measure, such as a heat transfer coefficient or something like this. So generally speaking, something that's good should have, in very few samples, get very high performance and have it continue across. Okay? So if we compare it just to traditional representations like parsec or NURBS, what we see is that in parsec, which is a much older representation of airfoils, that under both genetic algorithm, a GA, or Bayesian optimization, what we end up with is getting much slower convergence to smaller values of lift drag coefficients. If we do something like a NURBS description of the geometry, that does better, though still fairly slow. Alternatively, you could do a linear decomposition, something like principal component analysis or singular value decomposition, and there, as you might expect, you see a very rapid uptick in the performance, the optimums you're able to find, but then there's a kind of a plateau where that linear subspace is not allowing you to access portions of the design space that are higher performance. And this is the trade-off that PCA pays to be able to get that speed up. In contrast, what our Bézier representation does is, because it's able to model that subspace of good designs more compactly and also more faithfully, it's able to make rapid progress to finding reasonable designs, and then also not suffer in terms of the final design performance that it's able to achieve. And in this particular example, compared to these methods, it accelerates the optimization process by about 1 order of magnitude. Now granted, these are existing methods, so we can see how we now compare against something like other state-of-the-art methods that have been developed recently. So if we take a look at, for example, freeform deformation, which is often used in many existing adjoint packages for doing aerodynamic optimization, we'll see that both using GAs as well as using Bayesian optimization, that they have some improvement as you go up, which is good. Genetic modal variables achieve similar kind of performance to what you see here. SVD does surprisingly well on these problems, so just taking a linear subspace, again, as we saw in the previous one, tends to outperform ones that can't take into account ways in which the subspace is tied together. But then Bézier again is able to achieve in fewer number of samples greater lift drag coefficients because it's able to better model this lower dimensional subspace, and that in turn helps the optimizer find good quality solutions by limiting the number of variables that we have to search. Okay, so where do you go from here if I've convinced you that these techniques are reasonable to look at? Well, the first question you might ask is, what data do I need to make this work? So basically you need any prior data on the geometry or materials or other factors that you'd want to optimize for. And this doesn't necessarily have to be optimized designs. As you saw in the UAC airfoils dataset, those are not necessarily optimized for specific use cases. Those are just examples that help you sift through very high dimensional spaces to get approximately reasonable lower dimensional ones. In addition to this, if you have ways to augment that data with respect to invariance, say for example by rotating airfoils if you know they need to be rotationally invariant, or if you need, in the case of the hierarchical parts that I showed you before, if you're able to sort of move parts inside of this airfoil, for example moving conduits inside in order to represent geometric constraints, those are both ways that you can supplement the existing data that you have. If you prefer adjoints, which many people do for optimization, actually these methods can kind of complement what you're doing in those methods as well. For example, the structure that we generate with our Bézier GAN network, you could just take the generator portion of it without the discriminator, and you can actually flow your gradients from your adjoint backwards through the generator to do optimization, gradient-based optimization, directly on the latent space. They're not incompatible. What if innovative examples actually lie off the manifold? For example, we're learning this sort of subspace, but maybe the highest performing designs are actually off the manifold. They actually lie off the subspace. So it turns out that that can be true, but that these design manifolds can actually act as a great way of warm starting that search. So for example, you can first learn a sort of roughly optimal position on manifold, and then go back and explore and optimize in your original design space if you choose. Moreover, you can think about exploring on manifold, but just away from examples that you've already trained on. So basically moving outwards. In this example that we have in one of the papers, we give it a seed set of airfoils that are feasible in one area, and we have another algorithm called active expansion sampling that moves around and tries to capture other areas of the space that work well for this. When shouldn't you use this? Well, if you don't have any kind of reasonable prior designs or any other kind of past experience that highlights invariance that you can use to bootstrap those, then this is really not the right approach for you, right? So this, if you're working in a completely new kind of physics on a completely new problem where your company or research lab has never produced any designs remotely similar to this, then this is not going to be the right method for you. What you're going to want to use in those cases, if you have access to something like an adjoint method or be able to take gradients, is to use something like active subspaces or just traditional optimization. In many companies and people that we talk to, many of them have reasonable designs that they've had as a starting point, but maybe for different boundary conditions or different types of problems. In all of those cases, actually these methods work reasonably well. Okay, so how can you get started from this? One thing you can do is you can go to our lab's website here. You have our GitHub where you can get code and data associated with some of the papers that I've showed you here. And you can also go to our lab's website to actually read the papers themselves to get a sense of where and how these techniques might be useful to you. Okay, thank you everyone for listening to my talk today. These are some of the papers that I talked about in the work today. I just want to thank our funding from DARPA, the Office of Naval Research, the National Science Foundation, the National Institutes of Health, and ARPA-E for supporting this work.